Okay, so let's begin. Now it is post mid-sem, and we would like to gradually move towards more and more applications. Okay, so if you remember the NLP stack, okay, there are layers, and we start with morphology, go to part of speech tagging, chunking, parsing, and so on, all of which are foundational NLP tasks. They are foundational because they are used in all applications, all NLP applications. Of course, there is a different point of view or different situation because of the deep learning framework. But yes, these are really foundations. Now, we sort of started machine translation the other day, and machine translation will engage our attention for some time. This is really the what is called the forcing function for natural language processing. Forcing function means if you try to tackle machine translation, almost all NLP problems will need to be tackled. Okay, as I'll show you, and I think Saurabh also has shown. While tackling the machine translation problem, you encounter all the problems of NLP. Okay, that we'll see. And machine translation also can be said to have started the whole area of AI itself. Okay, a whole area of AI because there was this need in 1960s to do machine translation between English and Russian because of the Cold War between USA and Russia, and this gave rise to this need for automatic translation. And since translation is a human activity, requires a lot of expertise, domain knowledge, word knowledge, and so on. This was a representative AI problem. So machine translation became important from those days, and it was deceptively simple. People thought that the machine translation में क्या रखा है? You just take the word and substitute words in the target language, and you get the translation. Okay, but this was not to be the case, as lots of examples showed. And there is one story which is actually not an actual occurrence. Okay, this never happened, but people created this story to underline the actual problems in machine translation. The story goes like this. Maybe some of you have heard this. The story goes like this. There was an English to Russian and Russian to English machine translation pipeline. So there is this very famous biblical sentence which says the flesh is weak, but the spirit is strong. Okay, the flesh is weak, but the spirit is strong. So meaning thereby, the body may be weak, but the will and determination, these are strong. That is the meaning of the sentence. So this was translated to Russian and back to English. Apparently, the translation came out to be the meat was rotten. Okay, the meat was rotten, though the alcohol was very good. Okay. Now, one of the meanings of meat, flesh is really meat, and one of the meanings of spirit is alcohol. Okay, so this is a story which has been told umpteen number of times. I also like to listen to this story and also tell it. But apparently, there is no truth in this story because this is too much of a coincidence that both the words will exactly target a situation which is of physical nature. Okay, flesh will translate to meat in the round trip translation, and spirit will come back as alcohol. Okay, so what is the main problem then? Why is machine translation challenging? So how would you describe the challenge? Hmm. If you recall, right in the beginning, we said that the main problem of natural language processing is ambiguity. Okay, and here also we see ambiguity in operation. The word flesh has multiple meanings, and one of the meanings is meat. So somehow that meat meaning came from Russian and was translated back to meaning, back to meat when you came back from Russian to English. Okay, similarly for spirit. So one problem is lexical ambiguity. Words have multiple meanings. And you know there are two kinds of ambiguity. One is lexical ambiguity, words have multiple meanings. There is also structural ambiguity. Okay, the sentence can have multiple parse trees. So when we have multiple parse trees, again you can have multiple translations. No, and which one to choose is the disambiguation problem. I saw the boy with a telescope. मैंने उस दूरबीन वाले लड़के को देखा. I saw the boy with a telescope. मैंने telescope के द्वारा उस लड़के को देखा. Right. So any of the two translations is possible, which is due to structural ambiguity. Now we therefore have to solve these problems. And today's machine translation systems, which are based on deep learning, they solve this problem by neural network and softmax function. Okay, softmax gives you the highest probability option, thereby doing the disambiguation. Okay, let's proceed. Now, as our convention is, we do a one-slide recap of the week that went by. Of course, the week before was the mid-sem week, and today we'll have a look at the model answer to the questions. I'm a bit worried that the class average out of 40 is 4. Class average out of 40 is only 4. That's a bit strange, because the question paper was very easy. Now, there were 2 subjective questions where, of course, you get partial marks also. So let's see. Now, the one slide recap of the week of 9th September was this. We discussed the notion of domination. And I think one of the reasons why you could not do some of the questions is your idea of domination was not clear. Okay. The question paper was, when I say question paper was very easy, it is easy for those whose foundations are strong and clear. Otherwise, it is very difficult. Okay, so the assumption is that when you go through a course and sit in the class, look at the lecture material, study them carefully, your foundation gets built. That is the hope. Okay, so notion of domination was is a very important notion, because through that we create the probabilistic parsing framework. So as you can see, yeah. So from the notion of domination, we go to probabilistic parsing, where we ask, does the starting symbol S dominate these sentences? Okay, that means will we get a correct parse tree from this sentence applying the grammatical rules, and will the probability of the parse tree be high as far as the rules are concerned and the probability values are concerned? So probabilistic parsing framework is given in the form of a noisy channel formulation equal to argmax of probability of T given S. And after applying Bayes' rule, we come to the conclusion that the probability of the parse tree, PT, gives rise to the best possible parse tree, which is T star. Okay, T star is that possible parse tree whose probability is the maximum. So that was the very important idea conveyed. And the same probabilistic formulation will work for dependency parsing also. This we have sort of kept in the background for now. After some time, we'll come back to dependency parsing also, which is very important for Indian languages. Then probability of a sentence, all of you know, this is a very important concept, because probability of sentence is nothing but the language model. Okay, and large language models are again probabilities of sentences. And does anybody remember why large language models are called large? Hmm? Large sequence. The sequence is very large or long, and typically 4,000, 5,000 words. And the probability of that sequence needs to be computed, which we do through a large number of parameters in the neural network. Okay. And the in this framework, the probability of a sentence is equal to the probability of the sum of its parse tree. Now, many of you actually did not see in question number 3 that there were 2 parse trees, and that includes me also. So one of you, I think Rajshekhar, pointed to me that children in cars with toys has 2 parse trees. Okay, so many of you missed 2 parse trees, and therefore you lost marks there. And it is fundamental to have that competence to see how many parse trees a sentence has. Otherwise, no point doing this course. Okay. Now, children in cars with toys, the question is who has the toys, children or the car? Of course, you can come back and say, what is the meaning of cars having toys? No, there are toys inside cars. Yeah. And children with toys means children owning toys, having it in their ownership. So the probability of a sentence is equal to the sum of the probabilities of the parse tree. Okay, which is a very surprising result. A language model is equal to the sum of the probabilities of the parse trees. What is the linguistic intuition behind this? Okay, the language model is the probability of the next word, right? Prediction of the probability of the next word. Probability of the next word, what has it got to do with the sum of the probabilities of its parse trees? What is the connection? Okay, a good something good to think about. Okay, so give a linguistic intuition of this equation. The language model is equal to sum of the probabilities of the parse tree. Then we came to a number of very important formulae. The beta probability, you can see from the picture, the beta probability is the probability that Nj dominates P to Q. So that is written by this notation, beta J P comma Q. What is the probability that Nj, the non-terminal Nj, generates the sequence P to Q? Okay, and this beta probability, the interesting part of beta probability is that it can be recursively computed. The beta probability is the sum of all possible ways Nj can be developed, okay, into other non-terminals, and those non-terminals dominating smaller segments of the sentence. Okay, so you have the segment P to Q, and if the grammar is in Chomsky order form, then Nj will give rise to 2 non-terminals at most. And those non-terminals will dominate 2 consecutive segments of P and Q, which are smaller than P to Q. Okay, so this beta J PQ can be computed as the sum of beta values over smaller segments and the probability of the rule going from Nj to Nk and Nl, giving rise to 2 more non-terminals. And then the final parse tree, which has the maximum probability, is again recursively compute from the delta value, which is like our Viterbi algorithm. Okay, this is a dynamic programming algorithm. Then we talked about this Catalan number Cn. Why we worry about efficiency? We have to worry about efficiency because the number of parse trees can be exponential in the length of the sentence. Okay, so this is also a deceptive situation. We might think that there are only 3-4 parse trees possible from the sentence, but within the sentence there are sub-sentences which can have multiple parse trees. And so number of parse trees is given by the Catalan number, which is exponential in the length of the string. And we did a stress test for parsing through the buffalo sentence, where there are 7 buffaloes. And there was a question in the midterm involving the wrong parse tree of the buffalo sentence. And you had to identify a correct subtrees in this parse tree. So these were the main points covered in the week of 9th September. Now let's proceed. We think of machine translation now, which is an automatic means of converting sentences in one language to the sentences of the target language. So many of you have been using Google Translate, Bing Translate. All these are machine translation systems, okay? And they're all now based on neural machine translation framework. But in the initial days, it was completely rule-based. And I know of systems where there are 500,000, 600,000 rules for giving the method of going from one language to another. So there could be rules like this, that you should translate bank to bank, or to Nadi Tat, meaning river bank. There will be a rule of this kind, and the rule will say that if bank is in the environment of financial concept, which is again codified in a rule, then bank should be translated as bank in Hindi. And if the environment is non-financial, then it should be translated as Tat, Nadi Tat, Samudra Tat, and so on. So creating this is intricate work. Okay, it requires linguistic expertise as well as domain knowledge and task knowledge. Okay, so machine translation systems needed years of effort to get created. And they were very high accuracy, by the way. There is this Xerox machine system from English to French, very high accuracy system. And for a long time, this was the best possible machine translation system, even when statistical machine translation came. It is only in the range of 2015 or so, that neural machine translation upstaged rule-based machine translation of Xerox. But it was a lot of work, 25 years to come to that stage of machine translation. But nowadays, you can create machine translation system in a day if you get the parallel corpus. Of course, the ball now shifts to another code. Who gives you the parallel corpus? Now, it so happens that there are many sources of parallel corpus. For example, the parliament proceedings are in multiple languages. They are parallel. Okay, similarly, legislative assemblies and so on. There are many sources of parallels, newspapers. Okay, so from those parallel corpus sentences, you can create a machine translation system by machine learning. But to have really a good grip on machine translation, we need to understand what is the challenge, what is the complexity involved in machine translation. So that comes from language divergence. I saw from the slides of Saurabh that he covered language divergence, but this is so fundamental, I thought maybe we'll take another look at this topic. So languages express the concepts differently. Okay, each language has its own property. If you want to be a little more colorful, you can say languages have their own personalities. Okay, so has any of you thought about why in Hindi or Indian languages the verb goes to the end, while in English, French, and so on, German also, the verb stays in the middle? Okay, why? You can say it is some freak of nature. But have you thought about what is the effect of this in our communication, our cognition, and our worldview? Do people who speak Indian languages, let's say Hindi, do they have a different worldview than people who speak English, just because the verb is in the middle? Okay, And if you think this question needs little more, practical support, just look at Indian language newspapers. Newspaper headlines almost invariably place the verb in the middle. India, Bharat haraya Bangladesh ko. Headline. Newspaper headlines almost invariably keep the verb in the middle. Just take a look at this. I see it in Bengali newspapers invariably, Hindi newspapers also, but Tamil, Telugu, Kannada, Gujarati, you are likely to see the same thing happen. Why is it that if the language's canonical form is such that the verb goes to the end, for headlines, why do they come in the middle? Okay, and why is it that 90% of the languages of the world place the subject before the object? भारत भारत ने हराया बांग्लादेश को, बांग्लादेश को हराया भारत ने. Not much. The subject comes to the front. For headline, verbs go to the middle. These things need explanation. Oh, this is to capture the attention of the reader. Yeah, that's a good point. So if I'm used to seeing the canonical form, then if the canonical form is changed, I will be surprised. My attention will be drawn. I will be attracted to the headline. Good point. Yes. This is psychological evidence. Yes. Is there anything more? Context of the sentence as early as possible. Okay. So here, let me draw a picture. This will come when we do semantic role leveling. So this is a stage, okay? And there are actors. These are actors, okay? Actor A1, A2, A3. This is the stage. So the stage is the action or verb. A1 is subject, which is a noun phrase, and A2 is object, which is noun phrase, and A3 is, let's say, beneficiary, which is also a noun phrase. So to give an example, the stage can be give. Okay, the stage is give. And the subject is Ram, object is book, and beneficiary is Sam. Okay. So what is the thought being presented here? There is a give action, and the agent of the give action is Ram. What he gives is a book, and who receives the book as a beneficiary is Sham. That is what is being told. Okay, so languages which put the verb in the beginning, Arabic, for example, puts the verb in the beginning, it sets the stage immediately. Give, Ram, book, Sham. If I say it this way, then the stage is set that there is a give action, and then comes the subject, Ram, object, second position, third position is the beneficiary, Sham. Okay, so this, if you look at language from this point of view, actors and stage and the actors, then setting the stage makes sense. So I can explain the verb fronted languages. But why is that the subject comes before the verb. Okay, how to explain that? Okay, so something to think about. So you have some conceptual questions, thought questions to be resolved. One, why is language, what is the connection between language model and sum of probabilities of parse tree? What is the linguistic intuition behind this? Why do subjects predominantly come before objects? Okay. Is there a different worldview for people who use verb in the front or verb between subject and object or verb and at the end? Okay, these are deep conceptual questions. They are different from learning rate, momentum factor, okay, 20 megabyte of memory, which are engineering questions. Okay, these are conceptual questions, but they are also very important. Okay, so now here is an extreme example of languages differing in their expressions. So this particular English string, Finnish string, which you have seen before, okay, means this English sentence, I wonder if I should sit down for a while. Okay, and how will the machine translation system generate this English sentence from the Finnish sentence? One answer could be that you store this string in a table and just pick it up, which is fine. After all, the neural machine translation systems, which huge number of parameters, are essentially extremely large tables with probabilities, whether you like it or not. These are extremely large tables with probabilities, and there is a probability distribution. Okay. So when we look at the English sentence and look at the Finnish string, then I see mappings. And I believe alignment was briefly mentioned in Saurav's class, but alignment is such a fundamental topic. Okay, it is not only applicable to machine translation, it is applicable to question answering, sentiment analysis, everywhere. So much so that alignment is tackled by the attention mechanism, cross attention, self attention. These are all alignment tasks. So this Finnish sentence gives rise to, I wonder if I should sit down for a while. And sit is the main entity here. The stage is sit. No. Which is the main verb here? Which is the main verb in this sentence? I wonder if I should sit down for a while. Wonder. It is wonder. Okay. But what is the semantically important verb here? Sit. Okay. So when I say I would like to drink some tea, it is drink tea, which is main activity. Would like is semantically subordinate, but syntactically primary. Okay, so these are the morphemes which give rise to the words in the English sentence. Now, this particular abstraction has played a very fundamental role in whole of machine translation, and its relevance has not decreased at all, even in the neural machine translation era. This is known as the Vauquois triangle. So at the lowermost level, you have what is called direct translation. So direct translation means you just look at every entity in the input sentence and keep substituting them without any processing of the input sentence. So that is, and it is like table lookup. For every language element in the source sentence, you do a table lookup and do a substitution. This is direct translation. As you move up the lower, up the left arc or left line of the triangle, you are doing more and more processing on the sentence. Okay, And at the highest level, which is at the tip, you have complete disambiguation of the sentence. And this is called the deep understanding level. Deep understanding level, okay? And deep understanding level, everything is disambiguated. There is a semantic graph or representation from which you begin to descend on the right side of the triangle and produce the so if you go up the hierarchy, up the left side of the triangle, you do lots of NLP processing, which is why I said machine translation is an NLP complete problem. Lots of NLP processing happens on the left-hand side. If you look at this, you have graphemic level. Graphemic level means characters. And you will be surprised to know that there are machine translation systems which simply do character-to-character mapping. Okay, no concern for syntax, semantics, word meaning, nothing. Just character to character. When I heard this for the first time, this was 10 years back, and I had a PhD student who is now in Microsoft. He is Anu, and he created, he is responsible for this, lots of resources which come from AI for Bharat. Okay, one morning he told me, sir, we'll do character to character mapping. Okay. Ram gave the book to Sham. Ram ne Sham ko kitab diya. Just map the characters. R to Ra. A to A ki matra. At that level. Okay. And I was so shocked. Okay. Because you see, I give a lot of importance to meaning and semantics. And pragmatics, of course, the higher level of NLP. He said, no, all this is not necessary. And it is true. Okay. If two languages are very close to each other, they also share the lipi, that is the akshar, and extremely close. Let's say Bengali and Assamese, Spanish and Catalan. Then this works, produces some blue score, which is respectable. Transliteration preserves the sound. Translation preserves the meaning. So, right. So, if you convert BANK to ba, ikar, bindi, ka, this is transliteration, and it so happens this is also a case of translation. But BANK converted to tat is not transliteration. It is translation. So transliteration is sound preserving. Translation is meaning preserving. Okay. So you see, if you're going up the left-hand side, you have morphosyntactic level and syntagmatic level. Have you operated at the syntagmatic level? Have you? Have you done anything at the syntagmatic level? You did. You did that part of speech tagging assignment. Right. So if a raw sentence is given part of speech tags for the words, then some processing has happened. You have ascended some distance on the left-hand side, and you have created some annotation mechanically for the raw text, and that is some amount of analysis done. It is useful in machine translation. So when raw text is enriched by further information, it reduces the need for parallel corpora. It also reduces training time. Okay. So morphosyntactic level, you're doing morphology analysis. Syntagmatic level, you're doing parsing, shallow parsing, pause tagging, and so on. Syntactic or functional level, you are doing dependency parsing mainly, because subject-object, these are being identified. And then you go to lexicosemantic level, interlingual level, deep understanding level. So at every level, this ambiguation is done, and you get more and more precise information from the input sentence. Okay. Now, when you come down the right-hand side, again, you do lots of processing, ontological interlingua, semantico-linguistic interlingua, SPA structure and predicate argument, and so on. All these are generation tasks. Okay, and finally, you have got the text, which is the meaning of the source sentence. In between, you have C structure and F structure. C structure is constituency structure. The parse tree constituents. And F structure is dependency constituents. Okay. Ram gave the book to Sham. So gave the book to Sham is the verb phrase. This has to be translated properly. Where does the word ne come from? The morpheme ne come from? Where does ko come from? They come from F structure, knowing that Sham is the beneficiary, Ram is the agent of giving, and so on. Okay, so the right-hand side is generation, left-hand side is analysis. The right-hand side has become very important today because of generative AI. And generative AI does not do any of these things. There is no staged operation. What does it do? How does generative AI produce the text, which is at the final level? Huh? Yes. So it just consults a probability distribution. Now, tell me what is the next most probable word, and produce it in sequence. You've got the text. Then the question is, what is the relevance of C structure, F structure, etc.? If you don't have data, that probability distribution is meaningless. It is just rubbish. Absolutely. Until you have huge amount of data, you have to be mindful of these stages. And even if you have lots of data, people are realizing that to have a system which is controllable under my control and where explainability happens, you need to be mindful of all these stages. Okay. Now we illustrate the meaning of going up the left side of the Vauquois triangle analysis. So look at this sentence, John eats bread. In the Hindi sentence, you will have the order as John bread eats, because the verb will go to the end. Now this can be systematically organized. If you take the parse tree of the input sentence, John eats bread, and apply a simple rule that within the verb phrase, just interchange the position of the main verb and the rest of the textual material. Okay, so you know this, you know what happens here. Just interchange the position of head and modifier. You know this, right? In the constituency tree, if there are two siblings, let's consider Chomsky normal form only. If there are two siblings, one has to be a head, one has to be the head, the other is the modifier. Just juxtapose the positions of head and modifier and you have the correct syntactic order. Okay, so that is what was done when parsing was made possible. Then lots of people just applied parsing and converted the English sentence into the sentences order. Ours did it in the lab, and we have papers showing that if we change the English order to Hindi order, the blue score improves dramatically by several points. Why does it happen? Okay, something to be thought about. It facilitates alignment. And this is quite intuitive. You see, you have John eats bread, and John roti khata hai. Suppose by some processing you've got khata and hai together. You have put an underscore. So you have John eats bread and John roti khata hai. Won't the alignment be easier if there is positional correspondence already? Okay, first position goes to first position, second to second, third to third, and the alignment is automatically achieved. Okay, so if the target language sentences order is same as the source language sentences order, the alignment becomes accurate and easier to. Okay, so this was found to be beneficial. This requires some work on the source language sentence. That's why you go up the ladder on the left hand side of awkward triangle. And then you have to do what is called a transfer. From parse tree, you will have to take the parse tree on the target side and then generate the sentence. That's why awkward triangle. Awkward triangle plays an extremely important role in machine translation. Okay, so make sure that you always read the preamble of the question, even if you have to spend 5 minutes. It's okay. Huh? It removes a lot of headache going forward. Anyway, so as you know, from question number 1 to 6 was MCQ, and 7, 8 were subjective. Now, subjective questions you had to write on only one single sheet of paper. That way, your hands are tied. You have only that much of space available. Okay, first question. Consider the phrase, there is more than what meets the eye. Identify the NLP-related situations from below, which are best described by the given phrase. Okay. Now, on this, I think I've received 1 or 2 mails which have questioned the answer, but you can resend me the mail. We'll not spend a lot of time here debating. Okay, I'll just take a look at your mail and then act on it. Let's look at the answers as they are given now. So there is more than what meets the eye. The answers are C and D. The justification is that the meaning of the given phrase, that is, there is more than what meets the eye, is that the situation has hidden aspects that are not immediately apparent. Okay. C corresponds to the pragmatic ambiguity, where B's intent most likely is to say he did well in the exam. Now, what is meeting the eye here? A, did you do well in the NLP exam today? B, the paper was very easy. What meets the eye is apparently there is no connection between the two sentences. Okay, what is the more part? There is something which there is more than what meets the eye. The more part is this, the intent. The intent is B is saying I did well, most probably, because the paper was very easy. So what is unsaid here is, yes, I did well because the paper was very easy. So 4 or 5 words are missing. So that's why there is more than what meets the eye. And D is the meaning of the sentence. The cameraman shot the player when he was near the minister. What is meeting the eye? What is meeting the eye is 1 or more interpretations that you probably have in your mind. The cameraman shot the player, took the picture of the player, or killed the player maybe. Okay. So what is meeting the eye is maybe one interpretation, but there are multiple interpretations of this sentence. I'm told that this sentence has 14 meanings. 1, 4. So try to find out all 14 meanings. So this is the correlation between the answers and the situation they expressed by the phrase. Any major objection? Option A. Answer. Okay, what is meeting the eye? Large language models need extremely large computing resource, which is fine. And what is there which is more than what is meeting the eye? Prompt. Where is prompt being said? Large language models are used for various things, not only prompting, for fine tuning, for adaptation, many things. Hmm. So your point is that large language models need extremely large computing resources, something hidden behind it. I see. So just send a mail to me. Okay, I'll see. But it is not in the same class as C and D. Hmm. Okay. Then let's see the worst case time complexities of early parsing and CYK parsing. So here, some of you have made a very strange mistake, and that is possibly because your idea of complexity is not completely clear. Complexity is asymptotic. Okay, so both of them are order n cube. So some of you have written CYK parsing is order n cube into size of G, the number of rules. Okay, but you see the complexity is always in terms of the length of the input. Okay, by definition. And also asymptotically speaking, what is the behavior? So as n tends to infinity, there is no difference between k n cube and n cube. Grammar rule G will increase with the length of the input. Oh, hmm. No, the grammar is fixed. How can the sentence length increase? It can increase. The grammar is fixed. When I say grammar is fixed, I mean the syntactic rules are fixed. The dictionary is also fixed. Now, how can you make more longer and longer sentence? Only through recursion. Okay, only through recursion. So grammar size increasing with the length of the sentence is string, and this is an online situation. Okay, you are presenting the sentence to the model, and as the length of the sentence increases, you see that the time also increases in power of n, the length of n. Okay, so we can do some nitpicking, but the point is this: that both of them are order n cube. And I would like to ask, uh, how many of you actually studied the complexity of these two algorithms, their derivation and so on? You did for both? So you must have done this correctly. Oh no, what? Because of G. Ah, that's why. Oh, that's it. Please send a mail to me. Okay, with the justification. Okay. Question 3 was real trap. Okay. Consider the grammar. NP goes to NPPP or NNS with equal probability. So noun phrase can be a plural noun or a noun phrase followed by a preposition phrase. Then PP goes to PNP with probability 1.0. That is the only way you can expand a PP. NNS is going to these four words: children, cars, toys, flowers, with equal probability 0.25. P goes to with and in, only two prepositions with equal probability 0.5 for each. Then the value of log 2 beta NP. This required some attention to the lectures. Okay. So what is the definition of beta? What is this notation beta NP and the whole sentence here? What does it mean? So we know that beta NP will be equal to the beta value of both the parse trees. Okay. The or beta NP children in cars with toys will be essentially equal to the sum of the probability values of all the parse trees. Now this sentence has two parse trees. Okay, the first parse tree is NP-PP, then NP gets expanded to children in cars. And PP goes to with boys, with toys. Now, can you tell me where does with toys get attached to? Is it with children or cars? Hmm? Car. What is the rule? NP has two children. One of these has to be head, the other modifier. Okay. One of them is the head, the other is the modifier. The head of the head phrase will be attached to by the head of the modifier. So with, now what is the head of the preposition phrase? Has to be a preposition. So this is with. Okay. What is the head of the noun phrase? It has to be the other NP and PP below. What is the head of the third NP here, which goes through NNS? Children. Okay. So children has to be the head of the first NP, the top level NP. Okay. So with toys will get attached to children. So children have the toys. This is the first parse tree, and its probability value is 0.5 to the power 7 if you take the product of these values into 0.25 to the power 3. Right. So you must have taken all these probability values, multiplied them. The other parse tree is where the toys are in the car. This also happens to have the same probability value. So beta NP therefore is 2 into 0.5 to the power 7 into 0.25 to the power 3 and log to the base 2. So this is equal to 1 plus 7 into minus 1 plus 3 into minus 2, which is minus 12. The answer is none of the options. If you consider only one parse tree, the answer would be minus 13. Okay, so here the main point is that there are two parse trees. Now choose the correct option from below for the time complexity of obtaining the dependency tree from a given constituency tree. Assume the CFG is in Chomsky normal form. So the answer is linear in the number of nodes of CT. That is right. Why? The main task in creating DT from CT is establishing the head modifier relationship between appropriate pairs of words. Okay. Unlike constituency tree, the dependency tree links the words directly. So you have to find out the pairs of words which are linked. That is the main task in dependency tree. This needs noting the this needs noting the siblings and then going down the paths to hit the head of the head sibling and the head of the modifier sibling. For example, given NP goes to NPPP, the head noun under NP is linked to the preposition of the PP. So you will have to create a relation between prep, children, and in. Okay, here, children and in. I do not see the ball here. Yeah, you see children and in. Children is below NNS and in is below P. Okay, so the head of the NP is children and the head of PP is in. So you link with prep relation. What does it require? What is the algorithm? You will start traversing from the top NP. Okay, go hit NP. This second NP, you must process for finding the head. So again, you will traverse all the nodes and get children from here. Then you will go to PP and again traverse the paths for all the nodes to get the head. So this is visiting all the nodes once. So this is the complexity of the algorithm is order number of nodes in the tree. There was some email about 2 to the power d. Now the argument was that typically the parse trees are skewed. Okay, so see here a huge amount of parse tree is on the right hand side. This is right skewed, the one on the screen. So how do you say that the complexity is 2 to the power d? Okay. So here the number of nodes is being assumed to be ordered 2 to the power d. We are assuming a full binary tree. Now the question is, assuming full binary tree, is it correct? Notice that time complexity is always worrying about worst case time complexity. So in the worst case, you can have full binary tree. Okay. Can you give an example of a full binary tree for a sentence? Grammar is in Chomsky normal form, and the tree is full binary tree. What kind of sentence will be this? What about the tree for little children laughed loudly? Little children laughed loudly. This will be a full binary tree. Little children is the NP, which has 2 children. And laughed loudly also has 2 children, verb and adverb. So worst case complexity we are talking about. That is why 2 to the power d. Again, if you have written something, I know. Yeah, you can say it again. So you are saying that that is what you're saying. Complexity being order n. And acha, d is order log n. Does not necessarily mean n is order to the power d. I see. Okay, good. So have you set the main? Okay. And the argument is? Means let's discuss time complexity only. This is correct, right? On means limit time, whatever function of n, of course. Limit as n tends to infinity, time n tends to n. That is the definition of complexity. Okay, fine. I'll look at it. But I would also like to think from this point of view, the limit as it tends to infinity. Yeah, you have said the same thing in your mail. Can you please? Yeah, please send it. Hmm? Oh, oh, correct option. Oh, hmm. Okay, I'll do something about it. Huh? Okay, let's proceed. Okay, so please send a mail. Okay, question 5. What will be the log probability of the word sequence children in cars with toys? Assume the lexical probabilities as in question number 3. All transition probabilities are zero point 0.5 and are bigram probabilities. You have to consider hat and dot tags as sentence beginners and enders. So here you have to imagine a hat before the beginning of the sentence, and the sentence is correctly pause tag. Okay, because it is referring to the question number 3, where the parse tree is given, and parse tree is given means the pause tags are also given, and the lexical probabilities are given. So you have to imagine a hat here in the beginning. So then the part of speech tags this. For the current case, the pause tags of the words in the sentence, the transition probabilities and the lexical probabilities are given. So probability of hat, children in cars with toys, product of transition probabilities and lexical probabilities. So this is 0.56 times, because from hat you will go to children with 0.5, children to in 0.5, into cars 0.5, and so on. So there are 0.6, 0.5 transition probabilities. And the lexical probabilities are already given, which are first of all, NNS, the children, cars, and toys, and two prepositions, in and with. So cars, children, and toys give rise to 0.25, which is 0.25 to the power 3. And in and with are 0.5s, 2 times. Okay. So then uh, the log 2 probability is what you have here. Log 2 p, which is 6 into -1 plus 3 into -2 plus 2 into -1, which is -14. So these, I think most of you got. Quite a few got this correctly. Now, is there any way other than this method whereby you can get the probability of the sentence? What will be the log probability of the word sequence? Well, you might come back and say that the log probability of the sequence is nothing but the log probability of the sum of the parse trees. Sum of the parse trees probability. But notice that the question is asking you to make use of transition probabilities. Okay, so you'll have to make use of the part of speech tag here. Okay, now this question, of course, we are dealing with an extremely wrong parse tree here. Now, this sentence, as we know, means that buffaloes from buffalo are bullying other buffalo. Okay. So the main point here is to note the main verb. So that which is the main verb here that has been told umpteen number of times in the class. Hmm? Sixth buffalo, right? Sixth buffalo is the buffalo, right? And now we see here the subtrees to be which are correct. The first NP. Let me see. This cursor you can't see. Oh, you can see. Okay. So this NP NNS buffalo is correct. Sorry, NP NNP and buffalo is correct. Here buffalo is the name of the place. Then VBZ buffaloes is wrong. The second buffaloes is noun actually. And this whole subtree is wrong. Buffaloes, buffaloes. I can't parse it with that meaning. So this buffalo is the main verb, and here NNP going to buffalo is correct. This is a proper noun. NNS going to buffaloes is also correct. This is a noun again. And NP going to NNP buffalo, this is also correct. This is a proper noun buffalo. Nothing else is correct here. Okay, and I said you have to pick only the maximal subtrees. Okay, so if I did not say maximal, then you will have to consider NP and NNP buffalo to be two correct trees. The whole tree is correct, and its parts are also correct. So that you did not have to consider. How many of you remember that the sixth buffalo is the main verb? Oh, quite a few. I thought I saw many wrong answers for this. Now come the subjective questions. First, let me do the last one, which was the easier of the two. English verbs participate in morphological and syntactic processes as follows, illustrated with the behavior of the word walk. We have the tensed form, walked, walking. It is not a complete set. Walks also is there. Okay. Then modal forms, will, shall, would, should, can, could, may, might, walk. Then tensed plus modal form, have, had, would have, walked. Would have walked, had walked, have walked, etc. Can, could, will, would be walking. Might have walked, and so on. So you have to give a grammar or a finite state automaton. In fact, going to finite state automaton from grammar is easier. Okay, from finite state automaton to grammar is little more tough. So the grammar is as follows. First of all, you have to take care of the tense form, which is this. Verb phrase goes to VB, which is walk, VBS walks, and VBD walked. Okay, a verb phrase can be composed of a single verb form, which is only these three. Notice that only walking cannot form a verb phrase. Only walking cannot. It needs an auxiliary verb. Then we have a verb phrase which can be a be auxiliary verb. That means am, are, is, was, were, one of these. And the wing form. Wing form is walking. That is the only way a verb phrase ending in ing verb can be formed. Then we have to deal with the participle form, first participle form. So where you have auxiliary can be in three forms: have walked, has walked, and had walked. These are the only ways a participle verb phrase can be formed. Modal verb form is this way: will, shall, can, may, would, should, could, might can come as MD. And the verb now has to be in base form. You cannot have ing or ed form. The next form is where you have tense form and modal form combined. Will have walked, would have walked, should have walked, and so on. This VBD is required here, not VB or VBS or VBing or being. The grammar says that this is the form. Then MD be walking, might be walking, shall be walking, will be walking, could be walking. That is the only form possible. And then the last one is most complex, where you have could have been walking. You cannot say could have been walked. That's not allowed. So if you understand the phenomenon clearly, what are the different ways the verb phrase is formed? No false positive, no false negative. Okay, you will not admit any string which is not following the grammar. You will not leave out any string which is in the grammar. Then this is the grammar rule. It requires some thinking about the language phenomena. And question 7 was, I think, the most demanding, I would say, not complex. Where you have give a CFG grammar with left recursion for the task. You have to produce a list of elements separated by comma. So the rule is very simple there. This is the rule. L, the list, goes to list, comma E, left recursion. And L can also go to E. So you can substitute L by L, comma E as many times as you want. And then substitute E by word 1, word 2, etc. The list can have duplicates, but the words are unique. Okay. And then if you want to remove the left recursion, you have to introduce L1. L goes to E L1. And L1 goes to comma E L1. So introduce right recursion. And L1 goes to epsilon. Then E is as before W1, W2 up to Wn. Okay, so those of you who are comfortable with left recursion gets it quickly. The main point is probability. So if P1 is the probability of the first rule here and P2 second rule, then in the expanded set of rules, which removes left recursion, the first rule must be 1.0 probability because the production begins with the first rule. This is 1.0. Then simply transfer P1 to this, L1 goes to comma EL1, and P2 to L1 goes to epsilon. And E going to different words, the probability remains the same. The last part was proof of correctness by induction. So I wanted you to use induction. Induction is not necessary here, but you have to use induction there. And there, as is the formal procedure for induction, you have to first set up the base case. The base case is k equal to 0, no a's. So if there is a recursive set of rules, then you can form it this way: a goes to b, whose probability is q1. Okay. No, it goes to b, probability is q2. I thought I had corrected this. Okay. And the non-recursive rule also produces the same, okay, it should be q2. Same probability, 1.0 into q1, because two rules are applied here. Okay, then the hypothesis, you assume that the probability is same for both cases with KAs. And in the induction step, you have to deal with k plus 1 A's. And you can show that both the probabilities are equal because you're making use of the formula that PA goes to AA is equal to PA1 goes to AA1, and PA goes to B is equal to PA1 goes to epsilon. Just look at the derivation, please. Instead of my telling it, if you look at the derivation, it's quite clear. Okay. Why insist on induction? Many proofs involving machine learning require induction. I wanted to see if you people are comfortable with induction.